Okay, I'm going to go over some of these problems in your gas law practice number 1. Okay, so remember we have these equations up here that we talked about in class. So the first thing we need to do is figure out which equation we're going to use. Basically, you're just trying to figure out whether the question involves pressure, does it have volume in there, does it have temperature in there, and that will help you figure out which equation. So when I read this one, the highest pressure ever produced in a laboratory setting was about 2.0 times 10 to the 6th atmosphere. So this is a pressure. If we have 1 milliliter sample of gas, well, that's volume at that pressure, then release the pressure until it is equal to, so that's a new pressure. It says about room temperature, but it doesn't say anything about the temperature changing, so we're not worried about temperature. What would the new volume be? So we have pressure and volume. So that means we're going to use the P1 V1 equals P2 V2. We got to figure out which variable we're solving for. It says, what would the new volume be? So we're going to solve for V2. And we want to predict what's going to happen so we know if we did the problem right or not. So the pressure initially is really high, and then it goes down to just atmospheric pressure, 1 atmosphere. So if pressure decreases, what has to happen to this volume number so that these are equal to each other? Well, if this goes down, this has to go up. So this is going to have to go up. And we don't have any units we need to convert. We don't have any temperature that needs to be in Kelvin. The pressures are given in the same units. Doesn't matter what the unit is, they just have to be the same. So now we're ready to solve this one. I recommend rearranging this equation to solve for the variable you want before you put your numbers in. But if your algebra is good, you won't need to. So we want V2. So we're going to solve for V2. So P1 V1 equals P2 V2. We're solving for this, so we need to get this by itself on one side. So we need to divide both sides by P2, and then P2 cancels. So V2 is equal to P1 V1 over P2. So we're going to put those numbers in. Highly recommend you actually put the units too. So this initial pressure here, 2.0 times 10 to the 6th atmosphere, times V1, which is 1 milliliter, divided by P2, which is 1 atmosphere. So when we do this on our calculator, we're going to get 2.0 times 10 to the 6th. Atmospheres had canceled, so the unit is milliliters. So that is the new volume. And it was supposed to increase, and it did. It went from 1 milliliter to 2.0 times 10 to the 6 milliliters. So that's our answer for that one. Number 3, a sample of gas occupies 3 liters. Well, that's volume. 300 K, temperature. What volume would occupy at 200 K? That's temperature. Okay, so we have volume and temperature. So from the front, we're going to grab this equation because it just includes volume and temperature. It's asking for this new volume, V2. And since the temperature is going to decrease, in order for these to be equal, the volume is also going to decrease. Or you just think about what you know from gas laws. If the temperature goes down, the volume is going to go down. And do we need to convert any units? No, we don't have any. Temperature has to be in Kelvin. It already is. Okay, so you can solve this one of two ways. You can either solve for V2. So I'm going to do that here. Just to get V2 by itself, we're going to multiply both sides by T2 so that T2 goes away. So we have that here. The other thing you could do is cross multiply. You could cross multiply those if that's something you prefer. So V2 is equal to T2, which was 200 K, times V1, the initial volume was 3 liters, divided by T1, the initial temperature was 300 K, and we're going to get V2. So when we put this in the calculator, 200 times 3 divided by 300, you get 2. So 2 liters. And the volume was supposed to decrease, which it did. Okay, for number 4, part of the reason that conventional explosives cause so much damage is that their detonation produces a strong shock wave that can knock things down. While using explosives to knock down a building, the shock wave can be so strong that 12 liters, what we have a volume, of gas will reach a pressure of, so we got pressure. When the shock wave passes and the gas returns to a volume of, so we have a new volume, what is the pressure? So we have volume and pressure. So we're going to do P1 V1 equals P2 V2. What is the pressure now? So we're going to solve for P2. And the pressure went, or the volume went up 12 liters to 610 liters. So if our volume goes up, our pressure has to go down. So we're going to predict it's going to go down. And both of our units for volume are in liters. It doesn't tell us any specific unit for pressure, so we can keep it like that. So none here. Again, we're going to solve for P2. So if you rearrange this equation and solve for P2, P2 equals P1 V1 divided by V2. So we'll plug our numbers in. 3.8 times 10 to the 4th millimeters of mercury is our initial pressure. Our initial volume was 12 liters. Our final volume was 610 liters. So when we take 3.8 times 10 to the 4th times 12 divided by 610, we get 748. But we're going to want 2 sig figs because that's 2, that's 2, that's 2. So 750. And what's our unit? Well, these liters cancel. Millimeters of mercury. So that's how we do that one. Oh, I'm sorry. That's how we do that one. I'm going to leave that there for a second because I didn't realize the paper wasn't up in the camera view. You can pause it if you need to. All right, number 5. A gas system has initial volume and temperature. So we have volume, we have temperature, these two numbers. If the volume changes, so we do have a new volume, what is the new temperature? So we have volume and temperature. So from the front, we're going to use this equation here. Resultant temperature. So we're solving for T2. The volume goes down, but be careful here. Notice this is in liters and this is in milliliters. So this is smaller than that volume. So we know we're going to have to do some conversions here. Liters to milliliters or milliliters to liters. We'll talk about that. But the volume went down. So if the volume goes down, so this is smaller, then the temperature also has to be smaller. So we want to make sure that that number is smaller. And the other thing is our temperature always has to be in Kelvin. So we're going to do those two conversions. So let's take care of those first because those are going to be used in our calculation. It doesn't matter whether they're both in liters or whether they're both in milliliters. They just have to be in the same unit. So I'm just going to take the 317 milliliters and I'm going to convert that to liters. So 0.317 liters. The other conversion I need to do is for temperature. So 5.53 degrees Celsius plus 273.15 equals 278.68 Kelvin. They do ask for the final answer in Celsius, but we have to have it in Kelvin to use the equation. Okay, so we're solving for T2. I would strongly recommend cross-multiplying in order to rearrange this equation. Students are notoriously bad at solving for variables that are on the bottom of the fraction. But I will show you how to do it. I mean, this is just remembering your algebra. We want this thing from the bottom here. So you can do a couple different things. You could flip them both, and then it could be on the top. We're going to cross multiply, and then we're going to rearrange from there. So if we cross these, we have V1 times T2 equals, and we cross multiply these, V2 times T1. We're solving for T2. So we're going to multiply both sides by that. That cancels. So T2 is equal to V2 times T1 divided by V1. I'm going to write it down here so we have more room. So V2 was 0.317 liters. Remember, I had to convert that. Our T1, 278.68 Kelvin. We had to convert that. And our initial volume, or V1, was 9.14 liters. So when we do that, we get 9.67. Remember, it's Kelvin. So that's the answer, and that's correct. But they asked for it in Celsius. So now we have to do one extra step. 9.67 Kelvin minus 273.15. And we get negative 263.48 degrees C. So that's our final answer here. We predicted the temperature was going to go down, and it did. So watch this video again if you need to help you with some of these so you can solve a few more problems.